Hi everyone. In today's video, we're continuing our discussion on carbonyl chemistry. This time we're going to actually focus on a new location on our carbonyl compound and try to explore the reactivity of this particular position. We're going to focus on alpha carbon chemistry, and then we're going to reintroduce enols and enolates. So it's my intent that by the end of this video, you'd be able to identify the various positions on a carbonyl containing compound, predict the acidity of these alpha positions on the carbonyl containing compound. You're going to be able to prepare enols and enolates. You'll be able to identify what a keto-enol tautomer is, and also propose mechanisms for these tautomerization reactions under acidic or basic solutions. So the first thing we're going to look at is just how we notate the various positions of carbonyl containing compounds. So for example, take this particular aldehyde. So this is your acetaldehyde. And let's try to label all the different positions around this acetaldehyde. So the most obvious position is actually that position where we have the carbonyl group. So we call the carbon on that CO double bond the carbonyl carbon, and the oxygen the carbonyl oxygen. For aldehydes, you may call that proton bonded to the carbonyl carbon your aldehydic proton. And then we begin to number using the Greek letters alphabetically the positions and the proximity of every carbon with respect to the carbonyl carbon. And so the first carbon next to the carbonyl carbon is called the alpha carbon, and the associated protons that are bonded to the alpha carbon are called the alpha protons. And just for recognition purposes, what I have done here is also show you what this particular molecule will look like using our bond and line notation. So essentially your acetaldehyde has a carbonyl carbon, a carbonyl oxygen, and an alpha carbon. Okay, so now let's take the example of this longer chain carbonyl compound. I have color-coded things so you can kind of see where things lie. You can once again notate the various positions around the carbonyl containing compound using the same Greek letter formulation. And so by the rules we just described, that would mean that the alpha position on the left, the alpha position on the right, they are both alpha positions, so there are two alpha carbons, and then 5 alpha protons in this particular molecule. And so we define once again the positions with respect to the proximity to the carbonyl carbon. And then as we go further and further away from the carbonyl carbon, now you're in the beta position, which is one away from the alpha. You're in the gamma position, which is one away from the beta, and the delta position, which is one away from the gamma. And so, like we just mentioned, this Greek notation with respect to the carbonyl carbon is in Greek alphabetical order, so alpha, beta, gamma, delta, and so on and so forth. And so once again, just so you can see this from a bond line structure, which is what you will mostly be dealing with, here is the same notation on the bond lines. You have your alpha, both ones, you have a beta, your gamma, and your delta. Okay, so for the rest of the video, we're going to focus on the reactivity at that alpha position. So we're going to specifically look at the alpha carbon and the alpha protons on a carbonyl compound. And then what I would now ask of you is to recall the acidity of these alpha positions. So if you have a regular ketone or aldehyde, the alpha protons actually have a pK of about 19. So this is actually pretty low compared to other sp3 alkane carbons. And this has a lot to do with the resonance form that is drawn once you actually deprotonate the alpha position on this particular molecule. And then even more acidic when you have two ketones or two carbonyl groups that are 2 carbons away from each other, the actual protons in between have a pKa even closer to 9. So 10 orders of magnitude lower in pKa values are more acidic than the case where you have just one neighboring carbonyl group. So this proton is actually relatively acidic compared to other types of protons that are similar in the makeup. And it's actually this acidity that is the origin of reactivity at the alpha positions of carbonyl containing compounds. Because these protons can be somewhat acidic, you can use a strong enough base to deprotonate those positions and actually engage in reactivity at that position. And so the generic reactivity here is that you take the carbonyl compound with the alpha position, and then actually under either catalytic amounts of acid or base, you can form what we call an enol, which is formed from the disruption of this one of the CH bonds at the alpha position and then a protonation at the oxygen. So this will be the tautomer of your ketone that we drew down here. But once you get to the enol form, you can actually perform a reaction in which the alpha position then gets functionalized using some kind of functional group we're going to call X. So instead of a catalytic amount of acid and base, you can actually make this reaction work under strong basic conditions. To take a strong enough base, you can absolutely still deprotonate your alpha position. This time you form what we call an enolate. So the enolate would just be, once again, a tautomer, which would be your enol form. But now that proton that should have been added to the oxygen is not added. So you now have an anion form. And this reaction can still occur where we take some functional group, we're going to call X, can add on to the alpha position, and you form your product. But all of this rests in the fact that these alpha protons are acidic enough that under some basic conditions or even some acidic conditions, you can always get some enol form in there. And definitely under basic conditions, you can get your enolate. Okay, so now let's focus on the tautomerization reaction that we just mentioned. So your ketone or your aldehyde can tautomerize to enols under any amount, really any amount. It could be trace amount or concentrated amount of either acid or base. And so when we have this square brackets around these different acidic and basic species, we're really just saying that this could just be a really tiny amount of this in the solution, and your ketone or aldehyde would immediately tautomerize to your enol. So it's important to remember that tautomers are not resonance forms. So this is not a resonance form because you are indeed changing the bonding makeup of these different molecules. And so the alpha carbon has been deprotonated to form your sp2 carbon, and your carbonyl oxygen has been protonated. So these are two different constitutional isomers. They just happen to be rapidly interconverting between each other. This is why we call them a tautomer. So that's all reviewed. So I want to make sure that we're on the same page here. Okay, so that being said, typically the ketone or the aldehyde form, so this particular form with your carbonyl CO, is favored over your enol form. And that has a lot to do with just the strength of a CO double bond versus a CC double bond. The CO double bond is just stronger than the CC double bond. And so typically that was what we would see, a favoring over the ketone form over the enol form. And then to drive home the point, like I said, it really doesn't matter how neutral you think your flask is. There's typically some trace amount of acid or some trace amount of base in your flask. And so you always have a tiny amount of your enol in your flask, no matter what. And any amount of the enol in the flask, no matter how tiny, can still promote reactivity at that alpha position. Which is to say that the enol formation in your flask is not very easy to control or isolate because you're always going to be going back and forth between the ketone form and the enol form. So that being said, there are some enols that are favored over the ketone/aldehyde form. So for example, we call this diketone, in which the carbonyl groups are 2 carbons away from each other. The enol form is actually more favored than the ketone form, and so that's usually the major substance or the major species when you have your diketone in the flask. Same thing with your ketone that is conjugated pi system within a 6-membered ring. Well, the enol form is also certainly more stable and therefore the major component in your flask when you have this particular molecule within. And so the reason for this deviation in the norm all lies within how the enol is being stabilized. So on the left-hand side, your enol is actually being stabilized at the OH by a hydrogen bond with the vicinal carbonyl CO group. In addition, the pi bond that is formed, the CC pi bond, is resonance stabilized into the vicinal carbonyl CO bond as well. And so you have a combined hydrogen bond stabilization as well as conjugation stabilization that keeps the enol form being more favored over the ketone form. Likewise, on the right-hand side, your enol form enjoys aromatic stabilization, which is not seen in your ketone form, and that alone will push any equilibrium towards the formation of that benzene ring. Okay, so now what we're going to do is propose reasonable mechanisms for this tautomerization under both acidic as well as basic conditions. Okay, so under acidic conditions, how does a ketone form its enol? Well, we already know that under acidic conditions, it's very possible for your carbonyl oxygen to get protonated. And then doing so forms this oxonium ion, which is resonance stabilized with the carbocation on the right. Okay, so now that we've sort of activated in many ways this particular ketone, if you have like the water in the system, the water can absolutely, one, attack that carbonyl carbon, which we've already learned what that reaction looks like, but it can also deprotonate the alpha position of this particular carbonyl compound to form your enol. Okay, so the alpha position chemistry happens in concert with the nucleophilic addition that we've learned in the past, but we're just saying that another possible mechanism that does occur is that the water can deprotonate the alpha position and then your enol is formed. And so ultimately, you're dealing with two proton transfer events in which at first the carbonyl oxygen gets protonated and then the alpha carbon gets deprotonated. Okay, and so now let's look at the reaction under basic conditions. So you have your catalytic amount of base in the solution. That base can certainly deprotonate the alpha position of your ketone to form this particular carbanion, which once again is resonance stabilized into this alkoxide. And it's this resonance stabilized anion that we consider an enolate. Okay, well, because we're in a flask with a catalytic amount of base, so not that much, and it's typically not going to be that strong, the enolate can actually get protonated by a water in a flask in a proton transfer reaction to get you to our enol. So this time, the order of events is the alpha carbon first gets deprotonated, and then your carbonyl oxygen gets protonated. So note that really the difference between the reaction done under basic conditions and under acidic conditions is all about the order of events in your mechanism. So either the carbonyl oxygen gets protonated and then the alpha carbon gets deprotonated in the case of your acidic conditions, or in the basic conditions, those two mechanistic steps get flipped. And so you have your alpha carbon getting deprotonated first, you form your anion, and then your carbonyl oxygen gets protonated. So all of this is actually to say that if you had a strong ketone and you treat it with a strong enough base, you will be able to form your enolate and essentially isolate your enolate at that form. And so take this ketone and then we treat with a generic strong base, you get your enolate in the flask. So the question is, how do we control this reaction so that we can get to our enolates and essentially stop at our enolates in the flask? It turns out that we have all the tools for this. This reaction is inherently an acid-base reaction, right? Your ketone is your acid, and whatever base you put in the solution is considered your base. Your enolate is your conjugate base of your ketone, and then whatever the protonated form of the base is the conjugate acid of the base. So it's an acid-base reaction, which actually means that you can use your fundamental principles looking at the difference in pKa's in the left and the right-hand side of the equilibrium as a good predictor of the position of the equilibrium. Which is to say, for example, take this particular aldehyde, which has the alpha protons with a pKa around 19, and then treat that with an ethoxide. With respect to the alpha carbon chemistry, you would deprotonate the alpha position and then form your enolate as well as your ethanol. Well, the pKa of the alpha protons and the aldehyde is 19. And so the position of the equilibrium of this particular reaction is going to be towards the left-hand side, or the formation of the ketone over the formation of the enolate. So while you will still have some enolate in your solution, it's just not going to be that effective of a base to actually fully deprotonate your ketone or your aldehyde. On the flip side, though, take this diketone where your two carbonyl groups are separated by two carbons. That pKa has a pKa of about 9, which means taking the same base, your ethoxide, and you try to go through a deprotonation. Now that equilibrium is going to shift dramatically towards the formation of your enolates and then the reformation of your ethanol. And once again, the pKa's can tell us why that's the case. The pKa of your ethanol is 16, the pKa of your ketone is 9, and so you really have this dramatically shifted towards the formation of your enolate over your diketone. And so be careful, the substrate can actually indicate or tell you the direction of your acid-base equilibrium. But a smart choice of base will actually get even this less acidic proton to be deprotonated and never come back. So one key one is if you take sodium hydride, with your H minus, that's a pretty strong base, have it deprotonate this particular alpha position, well, you're going to form your enolate, and then you're going to release hydrogen gas out of the flask. So one, entropy is going to drive this reaction towards the formation of your product because H2 is leaving. Two, the pKa of H2 is 35. Compare that to the pKa of this alpha proton, which is 19. This reaction is going to go directly towards formation of your enolate, and the position of the equilibrium will basically be non-existent because essentially there's no turning back once you form that H2 gas that gets liberated from that particular solution. So very effective at forming your enolate is treating your ketone or aldehyde with sodium hydride, and you essentially will get a one-way reaction towards the formation of your enolate. Another common strong base used in this particular type of enolate formation is taking what we call lithium diisopropylamide. So that's your lithium, your diisopropyl groups, and here's your amide. The short form for this is LDA. So L stands for the lithium, D stands for the diisopropyl, and then A stands for the amide. So take LDA, you react that once again with this not so acidic alpha proton with a pK of 19. But because the conjugated acid of your base has a pK of about 36, this reaction is going to go directly towards the formation of your enolates, and there's really no coming back because of how different its pKa's are. And so you can use a really strong base and you can get the full deprotonation to form your enolates of even fairly unreactive ketones or aldehydes in your flask. But once again, looking at the top right corner, if you're using a really acidic proton, then you don't really need LDA, you don't really need sodium hydride, you just need the ethoxide, and this would essentially get you to the full deprotonation regardless. So as you may have been able to pick up on from just looking at the differences between enols and enolates, you might also conclude that enolates are more useful than enols. And that is indeed true. From a chemistry perspective, if you can make a nucleophile even more nucleophilic, then that's going to be a much more efficient nucleophile than having a neutral version, which is not so nucleophilic. Okay, so we can readily explain this looking at just the structure of your enolates versus the structure of your enols. So simply considering the charge of the system, your enolate has a full negative charge around the enolate, and it's secluded at the carbon and the oxygen. And so that full negative charge is going to make your enolate even more reactive than, say, your enol with a zero overall charge on that particular species. So that alone will tell you that the enolate is more reactive than enol. From a handling and control point of view, in addition, enolates can actually be isolated and stored for a short period of time. However, because of how rapid and how interconverting enols are, they actually cannot be isolated or stored. And so, for these two reasons, not only is the enolate have the full negative charge, but it's also something you can use from an experimental point of view in a much more controlled manner than your enol. And then finally, looking at your enolate more closely, you might even see that both the carbonyl oxygen and the alpha carbon both have that negative charge or shared negative charge on them, which means that both sites can act as nucleophiles, right? So you can essentially use either the carbon or the oxygen on your enolate as a nucleophile in your reaction. And so one example here is take your enolate where the oxygen has that negative charge, and then you can essentially imagine throwing in an electrophile into the flask, and then the enolate oxygen attacking the electrophile to then form this particular product. We call this mechanism where your enolate oxygen is the one doing the attacking or the nucleophilic attack, the O attack. And then, of course, your enolate carbon can certainly serve as a strong nucleophile and attack an electrophile to form this particular product. So you can actually get two different kinds of constitutional isomers depending on which group is attacking the electrophile. It turns out that because we know even though oxygen is more comfortable with that negative charge than the carbon with a negative charge is more nucleophilic than the oxygen with a negative charge, which means that the majority of the reactions that would actually occur is the reaction where you have your C attack, where the carbon position actually is the one that's doing engaging in a nucleophilic attack. And so for the rest of the chapter, really is we're going to focus on the C attack, and we're going to look at several reactions in which the carbon of your enolate acts as a good nucleophile and it engages in reactions in the presence of an electrophile. Okay, so that's it, right? So we're going to identify the various positions on carbonyl-containing compounds. So you should know what the carbonyl carbon is, the carbonyl oxygen, the alpha, beta, gamma, delta positions. You should be able to predict the acidity of alpha protons on carbonyl-containing compounds. You should now be able to prepare enols and enolates, right? Using the right amount of base, you can prepare an enolate, or just in any catalytic system, you can certainly prepare the enol. You should also be able to identify the keto-enol tautomers of different molecules. These are rapidly interchanging constitutional isomers, so you want to look for the ketone form and the enol form. And you should be able to differentiate between that and the resonance structure. And then lastly, you should be able to propose mechanisms for keto-enol tautomerization under acidic or basic conditions. Okay? So thank you so much for watching this video, and I will see you in class.